Welcome back. Last time we were exploring prime numbers and their distribution and all that. And today we're shifting gears a little bit
Yeah.
to explore another concept
Mm-hmm.
that I think is really critical for understanding the relationships between numbers and patterns.
Yeah.
And that is correlation.
Mm-hmm.
So
Correlation plays such a unique role in number theory because it lets us see these connections that would otherwise be missed.
so we're not talking about like relationships in the way we typically think, right?
Sure.
Like how can numbers even have relationships?
Right. It's not that they're friends or anything like that, but it's understanding how changes in one set of numbers might be tied to changes in another.
Right.
For example, is there a correlation between how large a number is
Mhm.
and the number of prime factors that it has?
I see.
That's the sort of relationship we can look at.
Okay, that makes sense. And I'm curious about, how did mathematicians even begin to like grasp this concept of correlation? Where did it all start?
Well, the journey began with Francis Galton, a polymath whose work laid the foundations for what we know as correlation today.
Okay.
And then his ideas were further developed by Pearson, who gave us the Pearson product moment correlation coefficient,
Right.
or PPMCC for short.
Pearson. Yeah.
Ah,
That name definitely rings a bell for my statistics courses.
right.
So PPMCC tells us how much two variables are related in a linear way.
Mm-hmm.
Right.
Yeah, in your way. That's key.
So does that mean it can miss relationships that aren't straight lines?
Yeah, that's a great observation. You're right. PPMCC focuses solely on linear dependence.
Okay.
So, for instance, if we calculated the PPMCC between the number of prime factors a number has and its magnitude,
Mm-hmm.
we might get a value close to 0.
Mm-hmm.
But does that mean there's no relationship at all? Not necessarily. The relationship might be non-linear.
So PPMCC might be a useful tool.
Right.
But it seems like we need other tools as well for
Mhm.
those more complex relationships.
Absolutely. That's where rank correlation coefficients like Spearman's and Kendall's come into play.
Cool.
And instead of looking at the values themselves, these coefficients focus on the rank of the data.
That's interesting. Can you give me an example of how that would work in the context of number theory?
Certainly, imagine we're looking at a sequence of numbers and their corresponding number of prime factors.
Mm-hmm.
We could rank the numbers based on their magnitude
Okay.
and separately rank them based on their number of prime factors.
Mm-hmm.
Spearman's or Kendall's coefficient would tell us how closely those two rankings align, even if the relationship isn't a perfect straight line.
So even if a sequence appears chaotic, these rank correlations could reveal some hidden order
Mm-hmm.
in how those prime factors are distributed. That's pretty cool.
Mm-hmm. It is. But remember, whether we're talking about PPMCC or rank correlation, a strong correlation doesn't automatically mean one variable causes the other.
Right. That's the classic correlation versus causation dilemma.
Exactly.
Just because we find a correlation between, say, the number of digits in a prime number
Mm-hmm.
and its frequency, we can't assume the number of digits is causing that frequency.
Precisely. There could be other factors at play.
Okay.
Perhaps certain properties of numbers with more digits make them more likely to be prime, but the number of digits itself isn't the direct cause.
I see.
Always remember, correlation is a starting point for investigation, not a conclusion.
So we need to be careful about jumping to conclusions even when we find a seemingly strong correlation.
Yes.
Are there any examples in number theory where this trap is particularly easy to fall into?
Well, one has to be cautious when dealing with sequences that have hidden patterns we might not immediately recognize.
Mhm.
For example, consider the Fibonacci sequence.
Yep.
We might observe a correlation between the position of a number in the sequence
Mm-hmm.
and its value.
Okay.
But that doesn't mean the position causes the value.
Right.
The relationship is governed by the underlying recursive formula, not a simple causal link.
That's a great illustration.
Yeah.
So when exploring correlations in number theory, we need a healthy dose of skepticism
Mm-hmm.
and a deep understanding of the underlying mathematical structures.
Exactly. Correlation is a powerful tool, but it's only as good as our ability to interpret it within the broader context of number theory.
This has been a great foundation for understanding correlation in number theory.
Mm-hmm.
It seems like PPMCC and rank correlation are two essential tools in our toolkit.
They certainly are. And just like any tool, understanding their strengths and limitations is crucial for using them effectively.
I'm ready to dive deeper into specific applications of these concepts within number theory.
Great.
What kind of fascinating patterns can these correlation measures help us uncover?
Well, one area where correlation shines is in statistical mechanics, which might seem surprising at first.
Okay.
But statistical mechanics, despite its focus on physical systems, relies heavily on mathematical tools that are very relevant to number theory.
That's intriguing. I wouldn't have immediately connected statistical mechanics to number theory.
Right.
How does correlation bridge that gap?
Well, in statistical mechanics, we use correlation functions to measure the order within a system.
Okay.
These functions help us understand how microscopic variables at different positions are related to each other.
So instead of looking at numbers themselves, we're looking at the relationships between physical properties that we can express mathematically. Can you give me a concrete example to illustrate this?
Imagine we're studying the distribution of prime numbers within a certain range. We could treat each number in that range as a site in our system and define a variable that indicates whether that number is prime or not. Then a correlation function could tell us how the primeness of one number is related to the primeness of its neighbors.
That's a great way to visualize it.
Yeah.
So even though we're dealing with abstract mathematical concepts like prime numbers, we can borrow tools from statistical mechanics to analyze their distribution and uncover hidden patterns.
Exactly. It's a testament to the interconnectedness of different branches of mathematics and how tools from one area can illuminate another.
This is already opening up new ways of thinking about number theory for me.
Great.
I'm excited to explore more about correlation functions and their applications in our next segment.
Me too. We'll delve deeper into how these functions can be used to understand specific problems in number theory and how they evolve over time, adding another layer of complexity and insight.
I can't wait. Until then, dear listener, consider the hidden correlations that might be lurking within the number sequences you encounter. We'll be back soon with part 2 of our correlation deep dive.
Sounds good. Welcome back to our deep dive on correlation and number theory. You know, as we delve further into this fascinating world of correlation functions, we encounter the work of Lars Onsager, a remarkable figure who really bridged the gap between physics and mathematics.
Onsager's name is familiar, but I can't quite place it. Can you remind me of his contributions and how they connect to our discussion on correlation?
Sure. Lars Onsager was a Norwegian-American theoretical physicist who made groundbreaking contributions to statistical mechanics, earning him the Nobel Prize in Chemistry in 1968.
Wow.
Among his many insights is the regression hypothesis, a concept with profound implications for understanding how correlation functions change over time.
Okay, I'm intrigued. How does a Nobel Prize-winning chemist's work tie into the world of correlation functions and number theory?
Well, Onsager's regression hypothesis essentially states that the way microscopic fluctuations in a system regress back to equilibrium mirrors the system's macroscopic relaxation behavior when perturbed from equilibrium. In simpler terms, it suggests that the way a system forgets its initial conditions at the microscopic level is analogous to how it relaxes back to a stable state at the macroscopic level.
Okay, I'm starting to see the connections. So applying this idea to correlation functions, are we essentially saying that how those correlations decay over time can tell us something about the entire system's evolution toward equilibrium?
You've got it.
Okay.
Imagine observing ripples in a pond gradually disappearing. The correlation function captures those ripples' behavior at the microscopic level. And Onsager's hypothesis links that behavior to the pond's overall relaxation back to a still, calm state.
That's a vivid analogy.
Yeah.
It makes me wonder, how can a system as deterministic as a physical system governed by mathematical laws exhibit a kind of memory in the first place?
It's a fascinating question. While the laws governing a system might be deterministic, the sheer complexity of interactions between countless particles introduces statistical randomness. Think about the distribution of prime numbers. Individually, a number is either prime or not. However, when considering the distribution of primes across a vast range of numbers, their collective behavior can be analyzed statistically.
So it's not that individual numbers are remembering anything, but rather that their collective distribution over time holds information about the underlying mathematical structure.
Exactly. And correlation functions capture that statistical memory. As time goes on, those correlations might weaken, reflecting the system evolving in ways that could reveal deeper patterns.
This is really making me rethink how I view these seemingly static mathematical concepts. It seems correlation functions provide us with a dynamic lens through which to study number theory.
Absolutely.
But how do we actually measure or calculate these functions?
That's where things get even more interesting. While we might not be scattering beams of particles like physicists do,
Right.
mathematicians have developed various techniques to analyze and calculate correlation functions in number theory. One common approach involves analyzing the spacing between prime numbers.
Spacing between prime numbers. Can you elaborate on how that helps us understand correlations?
Certainly. We can consider each prime number as a point on a number line.
Mm-hmm.
The distances between these points, the gaps between primes, form a sequence that can be analyzed statistically.
Okay.
By studying the correlations in these gaps, we can glean insights into the distribution of primes and potentially uncover hidden patterns.
That's fascinating. So we're essentially looking for correlations in the rhythm of prime numbers.
You could put it that way. And this is just one example. There are many other techniques, from using Fourier analysis to study the frequency of digits in number sequences, to applying probabilistic methods to analyze the distribution of divisors.
It seems like each technique offers a different perspective on the same underlying concept of correlation.
Absolutely. Each method provides a unique lens through which to view those hidden connections within number sequences. And by combining insights from various techniques, we gain a richer and more comprehensive understanding of the intricate relationships that govern the world of numbers.
This has been incredibly enlightening.
Great.
I'm starting to appreciate how correlation functions, a concept seemingly rooted in physics, can reveal so much about the seemingly abstract world of number theory.
And we've only just begun to explore the potential of this powerful tool. As we delve deeper into specific applications, I'm confident you'll be amazed by the insights we uncover.
I'm ready for the next level of this deep dive.
Okay.
What other fascinating applications await us?
In our next segment, we'll explore how correlation functions can be applied to understand specific problems in number theory. We'll discover how they can help us analyze the distribution of quadratic residues, the behavior of arithmetic functions, and even shed light on the mysteries of prime number races. Stay tuned.
Welcome back to our deep dive into correlation in number theory. We've established that correlation functions, a concept often associated with physics, can be a powerful tool for uncovering hidden patterns in the world of numbers.
Exactly. And as promised, we'll now explore some specific applications of correlation functions within number theory. These examples will demonstrate how these functions can illuminate various problems and shed light on fascinating mathematical phenomena.
Okay, I'm ready to see these concepts in action. What kind of number theory problems can we tackle using correlation functions?
Well, one area where correlation functions have proven particularly insightful is the study of quadratic residues.
Quadratic residues.
Yes.
Those are the remainders we get when we square an integer and divide by a specific number, right?
Precisely. For example, if we look at the squares of integers modulo 7, we get the sequence 1, 4, 2, 2, 4, 1, 0. These are the quadratic residues modulo 7. Now imagine we want to understand how these residues are distributed as we move along the number line.
Okay, I'm following so far. How can correlation functions help us with that?
We can define a function that assigns a value of 1 to a number if it's a quadratic residue modulo 7 and 0 otherwise. Then a correlation function can tell us how likely it is to find two quadratic residues a certain distance apart.
So we're essentially looking for patterns in the spacing of these quadratic residues. It's a bit like how we analyze the gaps between prime numbers in the previous segment.
You've got it. And what's remarkable is that these correlation functions reveal surprising structures in the distribution of quadratic residues. They show that residues tend to cluster in certain regions and are more sparsely distributed in others.
That's fascinating. So even though the concept of quadratic residues seems simple at first glance, correlation functions help us uncover a deeper level of complexity in their distribution.
Absolutely. And this is just one example. Correlation functions have been used to study a wide range of number theory problems, from the behavior of arithmetic functions to the distribution of prime numbers in arithmetic progressions.
Arithmetic functions. Those are functions where the input and output are both integers, right? Like the divisor function, which tells us how many divisors a number has.
Exactly. And by analyzing the correlations between the values of these functions at different points, we can gain a deeper understanding of their properties and how they relate to other number theoretic concepts.
I'm sensing a theme here. It seems like correlation functions allow us to move beyond simply calculating individual values and instead focus on the relationships and patterns that emerge across entire sequences of numbers.
That's a great observation. Correlation functions provide us with a lens through which to view the big picture of number theory, revealing the intricate connections and dependencies that make this field so fascinating.
This has been an incredible journey. We've gone from the historical roots of correlation to specific applications in number theory, uncovering hidden patterns and gaining a deeper appreciation for the interconnectedness of mathematical concepts.
And this is just the beginning. The field of number theory is vast and constantly evolving, with new discoveries and connections waiting to be made. Correlation functions are just one of many powerful tools that mathematicians use to explore this fascinating landscape.
I'm definitely leaving this deep dive with a newfound sense of wonder and a thirst for further exploration. Thank you for guiding us through this fascinating world.
It's been my pleasure. Remember, the beauty of number theory lies in its intricate patterns and unexpected connections. Keep exploring, keep questioning, and you'll continue to uncover the beauty and wonder that lie at the heart of mathematics.
Thanks for joining us on the deep dive. We'll be back soon with another fascinating topic to explore. Until then, happy exploring.